Hello and welcome back. In this video we're going to be making it so the AHCI driver can perform a read command so we can get some bytes from the disk. Alright, let's get started. So the first thing I wanted to cover was actually a bug fix that was pointed out by a member of the Discord server. In heap.cpp, in the combine forward function, the next equals next needs to be the last line in the function after we get the new length. So just move that to the end of the function and that should be fine. Alright, so back in AHCI.h, in our port class, we can create a new function, bool read, and we can take one uint64t sector, and this is the sector of the hard drive that we want to read, or that we want to start reading at. Then we have a uint32t sector count, which is the amount of sectors we want to read. A sector is a 512 byte section. Then we have a void pointer to our buffer, which is the buffer in which the information will be read to. Alright, then we can head back over to ahci.cpp and implement that function. So we can create bool port : read. Then we can add the parameters uint64t sector, uint32t sector count, and void pointer buffer. Now we need to split the sector into two uint32t's. So sector low equals casted to a uint32t sector, and then uint32t sector high equals casted to a uint32t bracket sector bit shifted to the right by 32 bits. Alright, now we need to clear the pending interrupt bits of the HBA port. So interrupt status equals casted to a uint32t -1. Now we need a struct called the host bus adapter command header. So the HBA command header pointer cmd header equals casted to a HBA command header pointer HBA port command list base. Then we can set the command header's command FIS length to equal, FIS by the way is the frame information structure, and it's used just to convey some information about the command that we're sending to the port. So the length of the FIS is equal to the size of the FIS reg h2d, which is the frame information structure register hardware to device struct, which we don't have yet, so we will need to create that, divided by the size of uint32t. And this is the command FIS size. Alright, now we need to create the FIS register hardware to device struct, so let's do that now. So back over in ahci.h, we can now create the struct FIS underscore register underscore h2d. And this is a struct used when sending information from the hardware to the device. So we have the uint8t FIS type, then we have the uint8t port multiplier, which is the size of 4 bits. Then we have the uint8 reserved 0, which is 3 bits, and then we have uint8 command control, which is 1 bit. Then we have a uint8t command, which is the command register, uint8t feature low. Now I won't go into too much detail about what all of these values are. They are available in the spec if you would like to learn about what they are, which the link will be in the description. Right, now we need some information about the LBA. I'm pretty sure it stands for linear base address, and this is to select the sector in which the bytes will be read from. So we have the LBA 0, then uint8 LBA 1, uint8 LBA 2, then we have uint8 device register, then we have the upper bits of the LBA, so we have LBA 3, LBA 4, and LBA 5, all uint8, and together that gives us 48 bits of address space that we can use, which gives us support for up to many terabytes of disk space. Then we have a uint8 feature high. So this runs in line with feature low. Don't ask me why they are separated like this because I don't know. Then we have the uint8 count low, uint8 count high, uint8 ISO command completion, uint8 control, and then we have 4 uint8s which are reserved. Alright, now that we have that struct, we can go back into AHCI.cpp, and now this should be working fine. And this should be size of and not size t. Now we need to set the command header's right bit to 0, indicating that this is a read. And then we need to set the command header's PRDT length to 1. So you can have lots of PRDTs and you can have lots of command headers, but this will be a simple implementation and we will just be using one of each. Alright, now we need another struct, the HBA command table, pointer, command table, and we need to create this struct, this HBA command table. So back in AHCI.h, let's create that struct. So this is struct HBA command table, and the first value is uint8 command FIS, which is an array of 64. So we have 64 bytes for our command FIS. Then we have the uint8t ATAPI command, which is the size of 16 bytes. Then we have 48 reserved bytes. And then we have an array of host bus adapter PRDT entries, which we need to create that struct. So this is the HBA PRDT entry array. Now we need to create the HBA PRDT entry struct. So let's do that now. Just above the HBA command table struct, we can do struct HBA PRDT entry. This takes a uint32 database address, then a uint32 database address upper, then a uint32 reserved 0. Then we have a uint32 byte count, and this takes up 22 bits. Then we have a uint32 reserved 1, which takes up 9 bits. And then we have uint32 interrupt on completion, which is just 1 bit. So in total, this is 2 uint64s wide. Now that we have that, we should be able to go back into AHCI.cpp and continue. So our command table pointer equals casted to a HBA command table pointer bracket command header command table base address. Alright, now we need to memset this all to 0, so memset command table 0 size of HBA command table plus the command header's PRDT length minus 1 times the size of the HBA PRDT entry. Alright, now we can set the database address of the PRDT to tell it to put the bytes inside of our buffer. So we can do command table PRDT entry 0 dot database address equals casted to a uint32t casted to a uint64t buffer. Then we can do command table PRDT entry indexed by 0 database address upper equals casted to a uint32t bracket casted to a uint64t buffer bit shifted to the right by 32. Alright, so we've set up the database address and the upper database address. Now we need to set up the byte count to tell the device how many bytes we want to read. And it can only read it by a multiple of the sectors. So we need to do something like this, command table PRDT entry indexed by 0 dot byte count equals bracket sector count bit shifted to the left by 9 minus 1. And this will give us 512 bytes per sector. And we don't have support for this yet, but we can still do it anyway. So PRDT entry 0 dot interrupt on completion equals 1. Right, we've set up the PRDT. Now we need to set up the frame information structure. So FIS register H2D pointer command FIS equals casted to a FIS register hardware to device pointer bracket the address of the command table, command FIS. Right, now we need the command FIS type to equal the FIS underscore type underscore register underscore H2D. Now we don't have that, so we need to create that. So there's quite a few that we can use. So we can create the enum for that in AHCI.h. So just anywhere we can create the enum FIS underscore type. And then we can do all of the types of FIS that we can create. So FIS underscore type underscore register underscore H2D equals 0x27. Then FIS type register device to hardware equals 0x34. FIS type DMA ACT equals 0x39. FIS type DMA setup equals 0x41. FIS type data equals 0x46. FIS type BIST equals 0x58. FIS type PIO setup equals 0x5f. And the last one we have is FIS type dev bits equals 0x a1. Now back in AHCI.cpp, that line we just typed will now work because we've filled it in. Now we need to set the command FIS command control. So we set this to 1, indicating that it is a command. And then we need to set the type of command that it is. So the command FIS command equals ATA underscore command underscore read underscore DMA underscore EX. So we have an ATA command of read DMA, direct memory address EX. So we need to create this define. So in AHCI.h, at the top we can create define ATA CMD read DMA EX 0x25. 0x25 is the number that we need for the read command. Alright, so that is now working. Now we need to set the LBAs, all of the LBAs. So the command FIS LBA0 equals casted to a uint8 sector low. Then the command FIS LBA1 is casted to a uint8 bracket sector low, bit shifted to the right by 8. Then the command LBA2 equals bit shifted sector low to bit shifted to the right by 16. Then the LBA3 equals sector high, not bit shifted. Then the LBA4 equals the sector high bit shifted by 8. And then LBA5 equals sector high bit shifted by 16. Now we need to set the command FIS device register equals 1 bit shifted to the left by 6 to set it into LBA mode, which is the mode that we want for it to be able to use our LBA here. And then we need to set the count low and the count high to tell it how many sectors to read. So the command FIS count low equals sector count and 0xff. Then the command FIS count high equals bracket sector count bit shifted to the right by 8 and 0xff. So really the sector count should only be a 16-bit uint, but that should be okay. Now that we have that, the last thing to do is issue the command. So we can do HBA port command issue equals 1. And this will tell the command to run. But there's a couple other things that we need to do to make sure that the read completes properly and that it's thread safe and all that sort of thing for when we get into multi-threading and stuff like that. Alright, so the first thing we need to do before issuing the command is to make sure the port is not busy before actually issuing it. So if some other task has use of this port, or if this port is not done, then we need to wait for it. So while 2 brackets HBA port task file data and bracket ATA underscore device underscore busy, or ATA underscore device underscore DRQ, and spin is less than 1000000, spin plus plus. Now spin is just a uint64, it's just a spin lock. So uint64t spin equals 0. So that's just so that we have a timeout, just in case the port gets stuck. We don't want our thread to be stuck forever. But now we need to define these ATA device busy and ATA device DRQ. So in AHCI.h, let's create those. So we can do define ATA device busy equals 0x80, and then we have define ATA device DRQ 0x08. So this just ensures that we don't issue a command while a command is already running. Alright, and then we can check if spin equals 1000000, which is the number that we defined here. Then the port is hung and we can return false, indicating that this read has not been successful. Right, so now that we've checked that we can actually send the command without a problem, we can issue the command. Now we need to wait until the command is finished before continuing. So basically we can block the thread until it's finished just so that we can read something, wait for it to be done, and then continue. We can build it into an asynchronous model in the future once we get the interrupts working with the AHCI, but for now we're just going to create a blocking single-threaded implementation. So while true, we can check if 2 brackets HBA port command issue equals 0, then we can break, meaning the command's done, the command issue has been set to 0. We can also check if there has been a disk read error, so we can check the if HBA port interrupt status and HBA underscore PXIS underscore TFES. So we need to create this define, just like with the others, so we can copy that, paste that in, so define HBA PXIS TFES, and this value is bracket 1 bit shifted to the left by 30. It's just easier to write it like this than to do 0B1 and then 30 zeros after it. So if the interrupt status and this bit has been set, then we have a task file error, and then we can return false because the read has been unsuccessful. And then we reach the end of the function and we can just return true. Right, so that's the end of our read function. So it's quite a lengthy function, quite a lot goes into it. So let's try and use it. So now we can do something like port buffer equals global allocator dot request page, and of course we need to cast it to a uint8t pointer, and then we need to memset that entire buffer to 0. So memset port buffer 0x1000, so we set that entire page to 0. Now of course we're only allocating a buffer of size 4096 bytes, so we can't read more sectors than that. That is 8 sectors. If we want to read more than 8 sectors at a time, then we will need to create a larger buffer, and that requires having a contiguous section of physical memory, which we can't get just yet with this request page function, because this function sequentially could return fractured memory. So if we want a larger buffer, we will need to create a request pages as opposed to a request page. Now we can do port read and pass in the sector that we want to read. So let's do 0. Then we can do 4 sectors and then pass in the pointer to the buffer. So port buffer. Right. Now that we have that, we can print the result of that to the screen. So for int t equals 0, t less than 1024, t plus plus, and then we can do global renderer dot put char port buffer indexed by t, and then after that loop we can just do global renderer dot next. Right, now let's try that and see if it works. Just make sure that this equals is a 2 equals, not a 1 equals. And now, as you can see in our first drive, we can see that we have the FAT12 partition information, which means we have read from the drive successfully. We have the no name of the partition, and then we have just some random junk, which is actually the starting sector of, well, 2 sectors of our operating system. So that's pretty interesting. I just wanted to say a quick thank you to my patrons. Thank you to my tier 3 patrons Rizit, Bobby Addison, and Kevin++. Thank you to my tier 2 patrons Coffeepot, Cole Fordorado, Cyrus Hilliard, Daniel Cosper, Daniel Solov, Dual Chem, Exceeded, Jim Borden, John M, Mad Max++, Michael Bush, Mike Atkinson, Nil, Sunsea, Tomy, Sando Apostolov, and thank you to my tier 1 patrons David Gonzalez, Justin, Kenneth Looney, and THX TNT the Gamer.